Okay, let's look at some of these application questions from your sample finding. So, 75-foot radio tower is attached to the ground with a guy wire anchored at 55 degrees to the horizontal. That to the horizontal means the 55 degrees is down there. How long must the guy wire be? So we're looking for that length of the guy wire. Since we have, in reference to this angle, an opposite side and a hypotenuse, we're going to be using a sine function. So the sine of 55 degrees we know is the 75 feet in ratio to that hypotenuse, the length of the guy wire. So multiply both sides by g, divide both sides by the sine of 55, and we get 75 divided by the sine of 55 degrees. Now that answer is a perfectly fine exact answer. If you want to come up with a decimal approximation for it, that would be fine. It would probably be, I don't know, somewhere in the 60s. But, since these are all application problems, they should be answered in sentences, so a decimal approximation is probably most appropriate. So something like the guy wire is 75 divided by sine 55 degrees, feet long, is fine. They don't have to be complicated sentences. But if you want to use a decimal approximation, go for it. A 2,500 pound SUV sits on a hill. So we've got a big mass on a hill. That hill is 35 degrees to the horizontal. What is the braking force required? Technically, this is a vector projection problem, which we didn't really do that much of. We didn't do projection at all. So this might be a little outside of the scale of problems that you would see. But the nice thing is, if we're clever, one of the reasons I left it on here is because if we're clever, we can do it without. So anyway, if we want the braking force, then we want the amount of force that is going down this hill. So we want the force in that direction. Now we know that this thing produces a force of 2,500 pounds going straight down. We're essentially wanting to decompose this into, okay, how much of that 2,500 is going down the ramp and how much is going into or being absorbed by the ramp. And the key here is that this 35 degrees has to be the same angle as this 35 degrees. Because if this is a right triangle and that's a right triangle, then if we track our angles, if we had a perpendicular there, this angle and that angle has to match this angle. So that angle down there has got to be 35 degrees. Or better yet, if that's a right angle, this is a right angle. So if that's 35, this angle is the same as that angle, which means this angle is its supplement, so we can track that to this angle and that angle. So if this angle is the same as this one, then its vertical angle is also the same as that one, so this angle has to be the same as that angle. However you want to track it. I know I threw a lot of different angle tracking vocabulary at you there, but either way, those angles have to match. So we could use fancy vector projection logic here, or just the fact that that angle is 35 degrees, and we know this hypotenuse is 2,700. If we wanted this amount of force going down that hill, well, in reference to the 35, this is an opposite side length, and that 2,500 is a hypotenuse again, so the sine of 35 degrees has to equal that force divided by the 2,500. So 2,500 times the sine of 35 degrees is going to be that amount of force. So we could do that, But again, this problem is really it's a force problem, so it's really a kind of more of a vector problem. So it might be something a little bigger than what you might see. So I might not worry too much about that problem. But you can see it is within some of our tools, but it might be a little tough. You need to build a ramp to the bed of a truck to load equipment. Your expert tells you that the gear can be pushed up a ramp as long as the ramp is no more than 20 degrees to the ground. So it's got to be pretty shallow or it's going to be too heavy. So 20 degrees to the ground. And so our truck bed is up here, and then our truck is a terrible drawing of a truck, but that's okay. The truck bed is 4 feet off the ground, so this is 4 feet. So we have to know how long to make this ramp so that it doesn't exceed that 20-degree limit. So how long should this ramp be? Well, we have a theme so far of sign questions here. In reference to that 20-degree angle, that 4 is an opposite side, and that length that we want is, again, a hypotenuse. So we know the sine of that 20 degrees is equal to the 4 over the hypotenuse that we want. And then just multiply both sides by L, divide both sides by the sine of 20 degrees, and we have an exact value. Again, if you've got the tools to get a decimal approximation for that, or either a calculator or a table of values, great, but the ramp is or needs to be 4 sine 20 degrees feet long is totally fine. Nothing wrong with that at all. And of course, this should be in a sentence too. The braking force needs to be whatever 2,500 times the sine of 35 degrees is. So sentences for all of these problems. So those are all sign problems so far. Hopefully we'll break out of that a little bit. They weren't all supposed to be sign problems. So, where are we? Ship leaves harbor. For all of these problems, I'm always going to recommend that we draw some sort of diagram, particularly for application problems. We want to make sure we see what's going on. So ship leaves harbor heading due east. So we're heading due east. So that's north, and we're headed due east. Traveling at 25 knots, that's 25 nautical miles per hour, so that's a speed of 25 nautical miles per hour. After an hour, it turns due north, so after an hour, it's going to turn due north. So if it went 25 nautical miles per hour for an hour, that means it went 25 nautical miles. A nautical mile is very, very close to what we think of as a mile. It's just defined a little bit differently, so a little bit different lengths. After an hour, turns due north and travels at the same speed for 2 hours, so it went 50 nautical miles. So it went 50 knots that way, 25 knots that way. At this point, what is the ship's bearing from the harbor? And the harbor's bearing from the ship. So essentially, if you wanted to turn back, what would your bearing be? What direction would we go? Or if you were at the dock or at the harbor, you're at the harbor, what direction would you have to go to get to the boat? Either way. So essentially, we need to find this angle and or the angles up here so we can answer the question in terms of the direction that we're going to go. I'm going to find theta first. That's a tangent question. We know the tangent of that theta has to be 50 over 25, or the tangent of that theta would have to equal 2, which that reduces. So a little tan inverse of 2 is going to give us some value. And of course, we'd either need some technology or a table, because that's not one of our standard angles. So tan inverse of 2 is, I'm in degree mode, so 63.4. So 63.4 degrees. And of course, that's an angle heading into quadrant 1. We know there would be another angle down here at 243.4 degrees. But we're clearly looking for this little acute angle, so that being 63.4 degrees is perfectly fine for us. That does mean this angle up here also has to be 63.4 degrees, because they're opposite interior angles. And if we want to find that other little angle inside there, it's got to be its complement. So that would be, what, 26.6 degrees, that little angle in there. The question is, if we're going to set bearings, we have to remember how our bearings are expressed. So if we're this boat up here, then we've got a compass on our boat that points north, south, east, and west. So if we're this boat, we have to turn and make this angle of 26 degrees. So we have to head that way and make this angle of 26.6 degrees. So our bearing would be face south and turn 26.6 degrees towards the west. So that would be our bearing to head back to the harbor. Remember, all our bearings will start with either north and south, and then tell us how far to turn, either east or west. Now, if we were down at this harbor and trying to head towards the boat, well, we would face north and turn that same 26.6 degrees, but this time towards the east to get up to the boat. So if we're the harbor, we would be facing north and turn that same 26.6 degrees, but we turned that 26.6 degrees towards the east from north. So north, 26.6 degrees east. So finding this angle is essentially our basic skills. Being able to translate that into nautical bearings is a little bit of its own skill. So, but that's why we had that in our section on vectors. So we want to make sure we're used to that. Okay, ramp ship. So we're at Jill and her balloons. Okay. So Jill's watching a balloon rise into the air from 100 feet away. You had a version of this problem a little bit earlier. She measures the angle from the ground to the balloon at 20 degrees, so that's 20 degrees. 10 seconds later, measured the angle at 34 degrees, so a couple seconds later, it's at 34 degrees. I've exaggerated that here. And we're specifically told in this one that that angle took 10 seconds to be produced. And we're asked, assuming the balloon went straight up, what's its average speed? Well, to find its speed is just distance over time. Remember, rate is distance over time. So if we know that distance, divide by 10 seconds, and we'll get a speed. The problem on your exam last time was a little bit simplified, just said find that distance. The speed thing here is just to make the problem a little bit more interesting, really. And angles are not quite as nice here, but that should still be okay. We've got two triangles here. We've got the 20 degree with the 100. So if we want this side, we want the opposite side, we have the adjacent side, so that's a tangent question. So the tangent of our 20 degrees is going to equal that opposite side we don't know. I'm going to call it distance 1 for that distance, divided by the 100 feet. So our distance 1 is going to be 100 times the tangent of 20 degrees. Then the other triangle, the larger triangle, is 34 degrees, but it's still 100 feet on that adjacent side. We just want to know what this other side length is, or what we're going to call D2. D2. But again, it's the same setup. It's still a tangent ratio. The tangent of 34 degrees is that D2 over 100. And we know it's a tangent problem because the sides we're dealing with are opposites and adjacents, and tangent deals with opposites and adjacents. So that makes D2 equal to, multiply over the 100, 100 times the tangent of 34 degrees. So if we want how far it traveled in those 10 seconds, the total distance traveled, that's going to be our D2, our 100 tangent 34 degrees, minus the D1, the shorter distance, the 100 tangent 20 degrees. Now again, that's an exact answer. Heck, we could even factor out the 100 if you wanted to write it that way. And be careful, don't think you're going to turn that into tangent of 14 degrees. We know that doesn't work, however tempting it might be. But either way, some decimal approximation might be nice. And again, if those were nice standard angles, we could do that. Or if we had some table, you'll probably have a table on your test. The tangent of 34 degrees minus the value at tangent of 20 degrees, all those multiplied by 100, gets us 31 feet. So the distance is 31 feet. So if we want the rate, remember rate is distance divided by time, so it's 31 feet in 10 seconds, or 3.1 feet per second. So the balloon went up at about 3.1 feet per second on average. Okay. Moving right along, that was Jill and her balloons. And we got some boats. Boats are fun too. So a customs patrol ship spots two boats in the water. So we've got a customs patrol ship. It notices two boats in the water. One is 500 feet away at a bearing, so it's somewhere way over here, 500 feet. At a bearing of north 40 degrees west, so facing north, it's going to be turning 40 degrees towards the west. So that angle's 40 degrees. And the other is also 500 feet away, but it is bearing north 20 degrees east. So north 20 degrees east, face north, turn 20 degrees towards the east. It's also 500 feet. So there's one little boat we can see over here. another little boat we can see over here. How far apart are the two boats? Well, the fact that they're both 500 feet away from us, they don't have to be the same distance. It's kind of fun, but it doesn't have to be that case. How far apart are these two boats? Well, notice this angle here, that total angle, would have to be 60 degrees. Well, this happens to be, just by coincidence, an isosceles, not an isosceles, an equilateral triangle. Because if these two distances are the same, these two angles have to be the same, which means they're both 60 degrees and that this distance is 500 feet. But that's only because this is exactly 60 degrees and these are both exactly 500. So if that wasn't the case, which it generally won't be, if we want to find this other side, this is a nice law of cosines setup. A squared has to be equal to the 500 squared plus the other 500 squared minus 2 times 500 times 500 times the cosine of the angle between them, which in this case is 60 degrees. So a squared equals 25, 1, 2, 3, 4, it's a lot of zeros, plus 25, 1, 2, 3, 4, it's still a lot of zeros. And cosine of 60, well, cosine of 60 is 1/2, so 1/2 times that 1/2 is just going to leave the 500 times 500, which is, again, 25 with 4 zeros after it. 1, 2, 3, 4, 1, 2, 3, 5, got an extra zero there. So that's going to make that a squared equal to, well, those essentially cancel, giving us 25, or 250,000. Square root both sides. The square root of 250,000 is 500. And that's that 500 feet that we expected to get because we knew this was isosceles, or equilateral, sorry. But that's just, again, because these match so nicely and this was exactly 60 degrees that it worked out quite this perfectly. Again, if these numbers were slightly off what they are, this tool would still work and would give us whatever the actual value is. So if you happen to notice you have this nice symmetric equilateral situation, you go, hey, that's got to be 500, go ahead and just put the 500, explain why, because it's equilateral. But if that's not the case, or we don't happen to notice that, it's nice that we can perform the calculations and find it. Okay, Billy's airplane. Billy's spinning the toy airplane on a 6-foot cord, so spinning it around on some 6-foot cord, and a little airplane on the end of that 6-foot cord, because that's got to be fun thing to do, right? And the plane goes around his body once every 2 seconds, so the speed is 1 rotation per 2 seconds, and we want to know what the speed of the toy plane is in feet per second. So we know it's how fast it's rotating. We want to get, okay, how fast is it actually moving on the edge there? So we want the linear speed in feet per second. Now we've been given an angular rotation speed, but we haven't been given the technical angular speed, because angular speed has to be in radians per second. So one of the things for us to do here is to convert this rotations per second into radians per second. But we know how many radians are in a rotation. We know there are 2 pi radians in 1 rotation. So if we multiply that, those 2's are going to cancel nicely, and we get pi radians per second after the rotations cancel. And that's our angular speed, omega, pi radians per second. And then we know linear speed, v, is equal to r omega, our radius times our angular speed in radians per second. So our linear speed is just 6 times that pi, and that's feet, and that's radians per second. So when we multiply those, we get 6 pi feet per second, because again, radians don't complicate things. So there are other ways to approach this problem. Like, we could find the circumference and do a whole bunch of extra work if we want to, but taking advantage of the direct relationship that radians give us, we can come up with this answer of 18 and change. It's about, 18.7, something like that. 18, 19, something. Fairly quickly if we take advantage of those relationships. So again, I didn't make a sentence for this one, but make sure you're answering all questions like this in a sentence. The linear speed is 6 pi feet per second is fine. But Billy's airplane is going 6 feet per second. Perfectly fine. Little Billy, it's a different Billy. This one's little, apparently. Little Billy is flying a kite. The kite string makes an angle of 53 degrees with the ground, which they have angelometers on your phones nowadays, so you could find that angle pretty easily. You used to have to build it with a protractor on a string and a rock, but now you can just do it with your phones. But we have a 53 angle degree with the ground. Billy has let out 100 feet of string, because that's how much string comes on an old-fashioned standard kite string roll. But of course, that doesn't mean the kite is 100 feet in the air, because it's at an angle. But Billy wants to know, in his adorable way, how high is this kite? So we want to know that height, h. And we're going to, ignore the idea of how tall Billy is. We're just going to say it's this far above you, Billy. Because, little Billy, he's not going to care. But if we had this is so far above an eye line, we could add that in if we wanted to. So we're looking for the side opposite our angle, and we have a hypotenuse, so that means this is a sine question again. So the sine of 35 degrees has to be that height over 100 feet, so that height had better be 100 times the sine of, 53 degrees. And just because I don't think Billy would like that answer, let's actually get a value for it. 100 times the sine of 53 degrees. Not that I'm saying Billy can't handle exact values, but that's around, 70.9, 79. So it's 80 feet. So it's approximately 80 feet. So Billy, your kite is like 80 feet high. Excuse me. And we're very excited for Billy, so exclamation point. Okay, and one of the, I think, nice points about this particular question is, we had a law of cosines question, we've had an angular velocity question, and this is back to just a simple right triangle trigonometry type question. So make sure when you're reading these problems, you're drawing a diagram so you know what you're looking at, and you're determining what the best set of skills are for this particular problem. You don't want to be using the big tools where we don't need the big tools. Save the big tools for the problems that need them. So it is common for people to try to kind of overcomplicate questions because they've just learned or just studied some of the big tools. So try to be careful of that. Bring the right tools for the job. So 100-foot radio tower, we've looked at these before. Sits at an angle of 70 degrees to the horizontal. Guy wires are attached 50 feet up and 30 feet down. So this distance is 50 and this distance is 30 in feet. And the tower itself is 100 feet. So, that would be, we could conceivably, somebody might say, hey, we know this is 50, we know this is 100. Pythagorean theorem would give us those other side lengths, right? Well, Pythagorean theorem only works when we have right triangles. So these aren't quite right triangles, so we can't use Pythagorean theorem. Because these angles are not 90 degrees. But we do know what those angles are, because we know this is, well, is it 7 degrees or 5 degrees? Always use the problem itself, so that should be 7. If you did this with 5, I wouldn't get mad at you, because I used the diagram from a different problem. But if that's 7 degrees, then this angle here is slightly short of 90. It's got to be 83 degrees, and this one has to be a little proud of 90, so that's going to be 97 degrees. So that's going to change our, Pythagorean theorem's not quite going to work. It's going to change our lengths. But the nice thing is, we have a tool for that. If we want this length, I'm going to call it A1. While Pythagorean theorem wouldn't work, law of cosines takes Pythagorean theorem and adjusts it for non-right triangles with that minus 2 times 100 times 50 times the cosine of the angle that's not quite the 90, so 83 degrees. So if we simplify this, if we just kind of evaluate this out, we'll get some big number. That's what, 10,000 plus 2,500 minus, what is that, 5,000 times minus 10,000 times the cosine of 83 degrees. So, you've done these. 10,000, 12500, is that right? 1, 2, 3, 4, 1, 2, 3, 4, minus 10,000 times the cosine of 83 degrees. Again, I've said this a lot. Be careful about subtracting those. It's so tempting. But at some point, we're going to approximate this. And again, you'll have either a table or there'll be standard angles. So 12,500 minus the product of 10,000 and the cosine of 83 degrees. Cosine of 83. And that's going to give us 11,281. 11,281. But that's still squared, so we make sure we square root both of those. We will get a plus or minus, but we know we're going to ignore the negative version. So 106. So the upper guy wire is 106.2 feet long. And if we wanted to find the lower guy wire, the process is exactly the same. That A2 squared is going to be the 100 feet squared, because that's one of its sides. This side is shorter, so it's only the 30 squared, minus 2 times 100 times 30 times the cosine of the angle between them. So the cosine of the 97 degrees. Sorry, that got into the problem there. And we could simplify it by, kind of by hand like we did over there. Or we can just type the whole thing in. Since I'm using a fancy calculator, I know you guys won't have the fancy calculators to use, but the numbers will be likely a little bit nicer just to, not make it terribly stressful. I don't want a problem to be wrong because you're just having to use those little calculators with big numbers. But I also want you to see practice problems that are of the right scale for the types of things you're going to be doing in calculus and physics and that sort of thing. 11,631.2, and then square root those. And again, as soon as we square root it, we get that plus or minus, which we will quickly ignore. So 107. And again, we're 107 feet. So the lower wire is 107 feet. So once you've got the right tool, once you know, oh, this is a law of cosine problem, these are my pieces, and this is what I got to plug into my pieces. These calculations are really just, calculations. You want to be careful about them. You want to get your order of operations right, not be doing weird subtractions. Don't forget to take its square root. Saying that the guy wire is 11,000 feet long would be kind of a weird answer, though I've gotten that answer on tests. It's always fun because people forget to square root it. But just be careful with those details. And frankly, make sure you're writing out what you're doing very nicely, because if I see this written out, I go, okay, they used the right tool, they used the right pieces, they're in good shape. And then, if by the time I get down here, some of these numbers aren't quite right because you've typed things in wrong or done a little bit of weird calculation wrong, so this final answer is off, that's not that big of a deal. It's just an oops in your calculations. You might lose a couple of points, but it's not the end of the world. So if I can see, hey, the right tool with the right pieces, and that's written out nicely, and then something goes wrong, okay. But if it's just kind of scratch everywhere and I can't tell what's happened, then I can't give you as much credit for that. So being in the habit of writing out what you're doing and labeling things nicely is really in your best interests. Okay, boat leaves harbor. We do like our boats here in Trig. Bearing south 48 degrees east, so facing south and turning 48 degrees towards the east. So they're going that way, assuming our standard compass rose. How many miles, for how long? Oh, 40 miles, there it is. So 40 miles. And then how many miles south of their starting position does it end up? So essentially, we're being asked for, it's hard to see, this distance. How far did they go towards the south? Okay, well, that makes a nice little right triangle. We want to know this distance, how far south. I'm just going to call that y since it's a y value. And so we've got 48 degrees there. I don't want to call it y because then I want it to be negative and all kinds of horrible things. I'm just going to call it d for distance. So in terms of this 48 degrees in here, we've got the adjacent side or we want the adjacent side and have the hypotenuse. So that's going to be a cosine question. The cosine of that 48 degrees has to be equal to that distance in ratio to the 40 miles. So multiply both sides by 40, and this distance is fairly nice. 40 cosine 48 degrees. No reason to make this problem any more complicated than that. Like I was saying before, read the problem carefully, draw a nice diagram, and decide what tool is best for the job. So the ship or boat is 40 cosine 48 degrees miles south is a totally fine answer. If you've got a table with 48 degrees on it and give a decimal approximation for that, or something else to give you a decimal approximation, great. But I love exact answers. Frankly, they make it easier to grade too. Okay, cart being pulled at a force. This is a work problem. I mentioned work in dot products, and we didn't get that far into applications of dot products. I know you've got some in your homework and so forth. Um, so we want to look at it. So cart being pulled with a force of 130 degrees, or 130 pounds at an angle of 23 degrees. So it's being pulled at an angle of 23 degrees to the horizontal, 23 degrees, being pulled with a force of 130 pounds, and the cart is going 100 feet across the ground, 100 feet. And work is our big dot product application. So work is supposed to be force. Often we say force times distance, but is specifically force dotted with distance. Because as we talked about in our dot product examples, that angle reduces the efficiency, that's fun, of our amount of work we get done. So not all that 130 pounds is going over that distance. So if we want to figure out how much work is done, we need a dot product to take advantage of that. So the distance as a vector is fairly easy because we're going 100 in the I direction and nothing in the J direction. So we don't need that 0J, but it's okay. The force, though, building it in trigonometric form is probably the nicest way. It's got a magnitude of 130, but then it's the cosine of the 23 degrees in the I and the sine of 23 degrees in the J. So that's our trigonometric form. But to perform the dot product, we really want the full component form. So 130 cosine 23 degrees in the I plus 130 sine 23 degrees in the J. So that's our force vector. We're going to dot that with our distance vector. And it's nice that it has a 0 in it because it's not going at some weird angle. And that's going to find their product giving us work and naturally accounting for the loss of force from that angle. So how do we find the dot product? You remember the dot product is the product of like components. So that 100 feet times the 130 cosine 23 degrees. Notice there's no i's anymore because this isn't a vector anymore, it's a scalar. So we're multiplying the components, not the i's and the j's. And then plus this 130 sine 23 times 0, which is nice because multiplying by 0 is going to make it go away. So that goes away, and we just get 13,000 cosine 23 degrees, and this is feet, and that's pounds of force, so it is foot-pounds, and that is our units for work. So if we want a decimal approximation for that, 13,123 cosine 23 degrees would be 11,966, 11,967 if we round, foot-pounds of work. I'm going to say is done. Sort of a sentence. So, if you're looking for an example of a work problem and a nice application of dot product, that is a nice, pretty standard application for dot product. How's our time doing? 44 minutes, okay. So that's our card. Ship, more ship problems. Ship leaves port bearing north 30 degrees east. So, north 30 degrees east. East is that way. So 30 degrees north, 30 degrees east. And what are we told about this ship? Told it travels 20 miles. The ship then turns on a new bearing, south 66. So this is going to get interesting. So it turns at a new bearing, south 60 degrees east. So that's 60 degrees. And travels 30 miles, so travels a little bit longer for 30 miles. How far is the ship from port and what bearing must be set to reach port? So we want this distance, how far is it away? It's not necessarily right on that axis, although I'm not sure if it's above the axis or below the axis. So that'll be interesting to find out. So we want that distance and what bearing has to be set to get back to port. Well, that's kind of weird. Since this is at 30 degrees, we know this has to be 30 degrees because they're opposite interior angles. That makes this a right angle. So that's fun. So, originally I was thinking this would be a law of cosines question. Because if this angle wasn't 90 degrees, then we'd need law of cosines to deal with that. But because that's 90 degrees, we just have, a 20 mile, a 30 mile, and we want to know, well, how far is this? And because that's a right angle, we don't need law of cosines. We just can use normal Pythagorean theorem. So that distance, I'm going to call that distance, squared has got to be 20 squared plus 30 squared, because that is our hypotenuse. Now, if this angle was anything else, we would just take 2, or we would just subtract 2 times the 30 times the 20 times the cosine of that angle. But because it's 90 degrees and the cosine of 90 degrees is 0, this whole term just drops away and we get normal Pythagorean theorem. So we could still do this if it wasn't 90, but the fact that it's 90 is nice. So d squared is 400 plus 900, or 1300 is d squared. So d is going to be the square root of 1300, whatever that is, and it will be plus or minus, but we're going to assign it the positive value only. So square root 1300 is 36. So 36 miles. So that distance is 36 miles. So that's the nice part, but trying to figure out what this bearing back is a little bit more of a trick. Now we have to be careful. It's tempting to go, well, this angle has to be 60 degrees because this is 30 up here. But we don't know that because we don't know exactly where this line is. We don't know if it's stopping below the axis or above the axis. With how I've drawn it, it looks pretty straight on. It looks a little bit above, but we don't know exactly where that is. I'm going to put it there just for sake of argument. So we don't actually know what this angle is. The only angle we know is this big one, is 90 degrees. But we can still figure out what this angle down here is. And again, I don't know if it's below or above the axis, but we can still figure out what this angle is because we have these two lengths. And we now have this length at 36. So because this is a right triangle, we can just use tangent to find this purple angle. But again, even if it wasn't, if this was some other angle measure, then we'd have an opposite pairing and be able to use law of sines to figure out that other angle. So either tangent or law of sines, either one will give it to us. And if we wanted to use law of sines, we could. I'll show you what happens if we ever used law of sines when we have a right triangle. It's just going to say the sine of that 90-degree angle in ratio to the 36 has to be the same as the sine of this angle we're looking for. I'm going to call it B in ratio to the 20. So it's going to look like a normal law of sines does. It's, you can use law of sines in right triangles if you really want to. It's just the sine of 90 degrees. The sine of 90 degrees is 1. So that just turns into the sine of B is equal to 20 over 36. Which is the same thing we would have gotten if we just went with sine instead, that being the opposite and that being the hypotenuse. Or we could have used tangent, or frankly we could have used cosine if we want. We have an abundance of information here because it's a right triangle. But all this would have worked without a right triangle using law of sines or law of cosines. Now I'd probably reduce this a little bit before I found the inverse, just because I like doing that. So that would be 5/9. You've gotten used to the fact that I like simplifying my algebra as much as possible. But then at some point we're going to need to take the sine inverse of that. So sine inverse of 5/9 is 33.7. I'm going to call it 34 degrees. So that implies that B is 34, did I say 34? Yeah, 34 degrees. And of course, or 146 degrees, because sine inverse always gives us, any of the trig inverses, always give us two answers in the first rotation. But it should be clear this cannot be an obtuse angle. If nothing else, it's opposite the shortest side of our triangle, so it's not an obtuse angle, so it has to be the 34, but as I always do, I make sure I consider both possibilities. So, we know, this is where it gets tricky, we know this is 60 degrees. That means this angle is 60 degrees. And we're told this angle is supposed to be 34 degrees. Well, that kind of tells us, well, this little angle here is supposed to be 34 degrees. Well, you might say, well, that's too many degrees. We've got that this is coming in 60 degrees to that, but when it leaves, it's 34 degrees. Well, that's because this point was, as it looks like it is, was above the axes, so it's pointing a little bit southward. So that's your 60, then there's another 34. So if you wanted to look at this angle, it's a little 4-degree angle there. Or more specifically, if we were going to face south, we'd have to turn 86 degrees towards the west to be heading back to port. Now that's a lot of little angle conversions in this problem, and if this was a problem on a test, which it certainly can be, but it would be a tough one on a test because of having to kind of control and convert all of these angles. So, it's perfectly a fair test question, but it's a tough one. And honestly, it's not a real good final question because it's a little difficult. But on a straight vector test, it would be certainly a valid question. But there is a lot of angle tracking going on in this problem that can be a little difficult, particularly if your experience with geometry is a little bit on the light side. But it is a nice application of our tools and a nice example of what, of how a lot of navigation works. And if you're trying to get, say, either a boat captain's license or a pilot's license, you have to be able to do these calculations even by hand. I've known some ex-Navy and ex-Air Force guys who were like, oh yeah, they made us do all that, because, computers go down, electrical systems get destroyed, things happen. So it's a nice type of problem to be able to work with. Okay, I do want to do this last one real quick. I am starting to run out of RAM in my little thingy here. So let's try to be nice to it. Let's see, we're on a merry-go-round that's rotating once every 45 seconds. That sounds like fun. So we're on a merry-go-round, and it's doing one rotation every 45 seconds. It's pretty slow. The wheel has a radius of 15 feet. That's pretty wide. How fast are you moving in feet per second? So this is one of those linear velocity questions. So how fast are we going on the edge of this thing? Well, just like the other one, we have rotations per time. So it would really be nice for us to turn this into radians per second, because radians per second has so much nicer of a relationship to velocity. So 2 pi radians in one rotation give us 2 pi over 45 radians per second after those cancel. And I don't want to reduce that at all because it doesn't reduce pretty. So that's our omega, our radians per second angular speed. And we remember that our linear speed, v, is radius times angular speed, or v is r omega. So we can calculate that linear speed literally just by taking the 15 feet and multiplying by the 2 pi over 45 radians per second. That will reduce nicely. And get a linear velocity of 2 pi over 3 feet per second. So that's about 2 feet per second, which is nice and slow. And, it's a merry-go-round. Merry-go-rounds are supposed to be nice and slow. So, how fast are you moving? You are moving at, I know there's no E, doesn't I? At 2 pi over 3 feet per second. Or approximate it if you want. Okay, hopefully that helps. I'm glad we got that in one video. That'll be nice. Do let me know if you have any questions on those. I know I went through those pretty fast to try to keep our time down, but if there's anything specific on them that you would like a little more help with, let me know. I'm certainly available. If you want to pick up your tests, those of you who haven't yet, I will be on Monday between 10 and 12. We'll be in the Learning Center on Monday. So even if you're taking your test on Monday, you should be able to come pick it up. If you want it, it is nice to review old tests. I know a lot of you haven't picked it up yet. Okay, I will see you later, and have a beautiful day.